All right, one-dimensional motion simply means that if you have an object that's traveling in a straight line, it doesn't deviate one way or another. We say that's one-dimensional motion. You can think of a train going straight along a track, or uh, somebody running a 100-meter dash. Um, but it doesn't always mean that it's a horizontal motion. It can be a up and down motion as well. So a ball being thrown straight up into the air, that ball is traveling along a straight line path. It doesn't have to travel left and right, it can travel up and down. So that would count as a one-dimensional motion. Or a skydiver falling to Earth follows a one-dimensional path. So all you have to do is think of it as a graphing idea where you have your x and your y, z if you want to throw in three-dimensional, but as long as it's traveling along one of those dimensions and isn't deviating, we say that it's one-dimensional motion. If it deviates, then we throw in another term called acceleration, but we'll save that for later. Now, when we're talking in physics about motion, whether it's one-dimensional or two-dimensional, you have to think of it in terms of a frame of reference. Your motion sitting in a chair is relative to the ground you're sitting on. You sit in a chair and you call yourself motionless because you're using the ground under you as your frame of reference. But if you used the sun as your frame of reference, you would not be motionless. You would be orbiting around the sun. The Earth itself is rotating on its axis, so there's really different ways to look at motion, and you always have to be careful about how you describe it. Are you using the ground as your frame of reference? Are you using the sun as your frame of reference? There's all kinds of ways you can look at it. So if I ask you something like, are you moving as you sit in your seat? Well, you would maybe respond, well, what are we using as our frame of reference? And of course, if I said the ground below you, then yeah, you would say you are not moving. So be careful when you describe motion in the course. Scalar versus vector quantities. In physics, we deal with both types. Scalar quantities are quantities that have magnitude only. Magnitude can be described as just the number with a unit. So if I look down here at these different quantities for scalar, you would see distance, speed, time, all these can be written as measurements, but temperature, direction has nothing to do with them. They're just scalar. So if I said something is 30 meters away, or if I said something is 28 degrees Celsius, that would be enough information for us. There's no direction that would follow degrees Celsius. It wouldn't make any sense. If I said it's 28 degrees Celsius north, well, that makes no sense at all. If something has a mass of 5 kilograms, then you're just giving a magnitude of the mass. There is no direction that you would associate that mass with. So all of these quantities down here that you see are considered scalar quantities, quantities that are just magnitude only without any direction. On the right, you notice that we have vector quantities. Now, vector quantities are quantities that involve not only the magnitude of an object, but also its direction that it's traveling. This is why if I said something like 30 meters, as it's written, it would just be a distance. But if I said 30 meters west, or 1.2 kilometers up, those would be considered vector quantities because not only do they involve the magnitude would be the 30 meters there and the 1.2 kilometers there, but they also involve direction. And if they involve direction with the magnitude, you consider them what we call a vector quantity. So let's take a look at some of these vector quantities. Displacement, vector quantity. This 30 meters west that I wrote would be considered a displacement. Don't confuse that with distance, because distance and displacement are not the same thing. If you think of a distance, you're not concerned about where you started. You're just concerned about how far you went. So you could leave your chair that you're sitting at right now, come back tomorrow, sit in the same chair, and you have gone a certain distance during that time. But displacement is different. Displacement is something totally different. It's where you started and where you ended up, and the difference between those two values. So we'll get to that in a little bit. But these values, displacement, velocity, acceleration, force, weight, moment, these are all examples of vector quantities. And of course here we see the vector character from Despicable Me, and I believe his tagline was committing crimes with direction and magnitude. I think that there's a link to that if you download the PowerPoint. And think about a air traffic controller. They have to deal with vectors all the time. They not only need to know how fast the plane is traveling, but they also want to know which direction it's traveling. Or a meteorologist, same sort of idea. Meteorologist wants to know where a storm is traveling, not just how fast it's moving. So be careful with vectors versus scalars. All right, displacement, we talked about this a second ago. It says the length of a straight line drawn from an initial position of an object to the object's final position. So we have a nice formula written here. Displacement is the final position minus the initial position, but here's the summary of the formula in symbol form. Delta x, that means change in position. So the delta x means change in position. XF really should be written with a subscript. It should look like that. And the XI should look like that. Something happened in the transfer to the computer's program, I guess. But XF, final position, XI, initial position. So the difference in those two is the change in position, the change in position. So I ask you a question to think about. Can the distance traveled ever be less than the magnitude of the displacement? Can the distance traveled ever be less than the magnitude of the displacement? Well, think about that. If you travel from point A to point B, you have gone a certain distance from here to here. Your displacement is how far you went from your final position from your initial position. But if you think about it, displacement can be zero. Even if you put a ton of distance on a trip, your displacement can be zero. So the distance traveled can never be less than the displacement. It can be the same and it can be more, but it can never be less than the displacement. Think of it like this: the distance traveled will always be equal to or greater than the magnitude of the displacement. Remember, when we say magnitude of displacement, we mean the number, like I say 30 meters west. The 30 meters is the magnitude. So if you travel a certain distance, the distance can never be less. It's always going to be equal to or greater than the magnitude of the displacement. If you think of it using the formula, it makes it a lot easier. All right, so there's different ways to represent directions. You can do Cartesian coordinates, which is like a graph. You can see x is along the horizontal line and y is along the vertical, and positive is in the direction where you would expect, and negative is in the directions that you would expect. Relative directions, right, left, up, and down, very easy to understand that. And then, of course, cardinal directions, like a compass, so north and south and east and west. Any of these are acceptable for directions in physics. And it really just depends on how how the problem's described. The problem may include positives or negatives. And you might see something like positive 30 meters. Well, that's 30 meters, that's a magnitude, and you see the positive sign, so that indicates a direction to the right. And you see the little positive to the right there. And as long as you're consistent in the problem, it really doesn't matter how you describe the direction, as long as if it's a vector quantity that you put a direction on it. So if I said 30 meters north, or if I said 30 meters down, or if I said negative 30 meters, those are all acceptable vector quantities. Now, of course, north doesn't necessarily mean down on the graph, and negative doesn't mean north. If you look at the graph here, it might mean down, but as long as you're consistent in the problem you're working on at the time, it doesn't matter what you call negative or positive, as long as you're consistent throughout the problem. And if you want to change it going to the next problem, you can switch it up. It's up to you. So let's look at a really easy problem. At least I think it's pretty straightforward. If you have an initial position of 10 and you have final position of 40, most of you probably could look at this and say, the displacement's going to be negative 50 meters. Now, if I said that the displacement is 50 meters, if I just wrote 50 meters, then all I've given is a magnitude, and that does not count as a vector quantity. If you're going to call this a displacement, you need a direction on that 50 meters. Now, if you can't look at that and reason it out, think about it using the formula. Remember, we have delta x, which is our change in position, is equal to our final position minus our initial position. Well, what is our final position? Our final position is negative 40. So negative 40 meters minus our initial position. Our initial position was 10. We started there, so that's our initial position. And negative 40 minus 50 gives us, negative 40 minus 10 gives us negative 50 meters. So that is why we would say that that is a negative displacement, because it simply means that I went to the left or in a negative direction or west, depending on how you want to describe it on the picture. Now, if we knew that to the left was west, maybe we could write 50 meters west on there, but they don't give us any information about that, so we don't really know if that's the actual direction. Or if I just wanted to say 50 meters left, because I'm left of my original position, I could do that as well. But because these numbers are given with negative values on the number line, you probably would want to use negative for your direction here. But it's not a quantity value, it's just the negative means direction. Just to review, is displacement the same as distance? Well, you should already know that it is not. The distance is the actual amount of ground you covered from one place to another. So let's think about just a quick little idea here. If I start here, so this is my starting point, and I finish here. So here's my finishing point. And I go here to here to here to here to here. I'm looking around, having a nice little hike, going this way, going this way, going this way, and I finally get to here. All of this ground covered that you see, that I drew in the red line, would be considered part of the distance I traveled. The distance from, or the change in position from here to here in black would be my displacement, okay? So the displacement here is just this straight line path that's in black. The distance is every little bit in red that I covered. Every part that's covered in my distance is considered in the value. So you might go to school. Let's say you get up in the morning, go to school, do your thing, go back home, have dinner, go back to bed, and you end up having a total displacement of 0 because you started your day getting out of your bed and you end your day in your bed. So your total displacement is going to be 0, but the distance you traveled is a lot because that's the distance that you go from your house to the school, back to the house. So they're definitely not the same thing. Distance is scalar and displacement is vector. Now, when you look at, say, an odometer in a car, which is something that you use to figure out how far you've traveled, well, I've kind of given away the answer in the way that I described it, how far you've traveled. What is an odometer? Is it displacement or distance? Well, hopefully you described it as distance, because if your odometer was displacement, then every time you got back home for the day, it would read 0. So a car odometer is definitely a distance value, not a displacement value. All right, so we're going to just look at this cross-country skier, and we're going to determine how much she had for distance and how much we would describe the displacement. She starts at point A at 0 minutes, and after 1 minute she's gone to point B right here, and then another minute passes by, and at 2 minutes she's at point C, and then another minute passes by, and at 3 minutes she is at point D. So she finishes at point D and she started at point A. So let's find the displacement for that. Well, we know that displacement equals the change in position equals the final position minus the initial position. Looks like her final position is at 140 meters. Now hopefully you can see that from the way the number line works. You have 40 meters right here. You have 100 meters right there. So that's 140 meters minus her initial position. Now her initial position, I would say, we'd keep it simple and just say that this was 0 meters where she was starting. So if she started at 0 meters, then her total displacement is going to be 140 meters. Now I've purposely made a mistake here. I said the displacement is 140 meters. Does 140 meters have a direction? No, it does not have a direction. So you would want to include some sort of direction in this. Well, perhaps we have a compass and we know that she was traveling due east. Well, then you could put 140 meters to the east. Or you could use Cartesian and say she was traveling along the x-axis. And if she was traveling along the x-axis, it looked like she went along the x, and it's in a positive direction, so we could say positive 140 meters was her displacement. Or we could just say she's traveling, say, to the right. And I could say 140 meters to the right. All those would be acceptable for saying that that was her displacement. Now the distance, remember, is just how much ground she covered. So let's take this step by step, and we'll just add them up as we go. From A to B, how much did she cover? Well, it looks like she went 40, then 100, and then 40. So that's 100 plus 40 plus 40. That's what, 180. And then from point B to point C, she went 40 and 100. So that's another 40, another 100. So what do we have there? That's 8 plus 4, that's 320 so far. And then she went from point C to point D, and that was 100. So what's 320 plus 100? That looks like 420 meters would be her distance traveled. Notice I'm not worried about direction here. I just am worried about the ground that she covers. So I just wanted to know the scalar value, the distance that she traveled. In this case, it would be 420 meters. So as we can see, distance, displacement, not even close to the same number. All right, this problem, a similar problem to the previous. Looks like we have a coach who is maybe walking along the sideline at a football game. And at point A, at 0 minutes, he's at the 50-yard line. And then it goes 3 minutes, and he walks from point A to point B. And then after 3 more minutes goes along, he walks from point B to point C. And then it looks like 6 minutes to 10 minutes, that's 4 more minutes go by, and he ends up at point D. So let's go ahead and do the displacement for this. The displacement, well, again, we're going to use our formula here. Change in position, that's supposed to look like a triangle, equals the final position. Well, what was his final position? Looks to me, if this is 10, and this is 5 yards, this is 0, this looks like a -5 there. So his final position is -5 yards minus his initial position. What was his initial position? Initial position was 50. So what's -5 minus 50? Well, that would mean a change in position of -55 yards. And we see we have exactly what we need here. We have negative for our direction, and 55 yards is our magnitude, so our displacement would be -55 yards. And then how would you go about solving for the distance? Well, the distance, again, we just add the numbers up as time goes by. So from 0 to 3 minutes, how far did he walk? Well, it looks like he walked from the 50 all the way to the 15-yard line. So to me, that's 35 yards. So he walked 35 yards from point A to point B. Then from 3 minutes to 6 minutes, he walks from the 15-yard line to the 35-yard line. That looks like another 20 yards. And then from point C to point D, he walks from the 35-yard line all the way to the -5. So that looks like 40 yards. And then we add up all of those numbers, and we end up with 95 yards for our total distance. So again, as you can see, 95 yards, there's no direction there, it's just a scalar quantity. And then -55 yards is the direction with the magnitude for the displacement. Hopefully that's pretty straightforward. All right, so now let's discuss our differences between average speed, instantaneous speed, average velocity, instantaneous velocity. Well, hopefully you recognize speed as being a scalar quantity, so no direction required. And of course, velocity is a vector quantity. And then you see the words average versus instantaneous in front of each one. It's a pretty straightforward difference between them. Well, let's just define speed. We haven't officially defined it yet. Distance over time, you'll notice that the term distance is used instead of displacement. Remember, they are not the same thing. Distance is the amount of ground you cover, whereas displacement has to do with the difference between your final position and your initial position. So be careful with the use of the word distance when you're talking about velocity. You use displacement, not distance. So S equals d over t. simple formula, speed equals distance over time. And any kind of distance time units are gonna work for a value. Typically in physics, we of course use a meter per second, but you could also say miles per hour would be appropriate, kilometers per minute. Any time unit will do, and any distance unit will do. Centimeters per millisecond is even acceptable. But the most common one that you'll see used in here is meters per second. So what is instantaneous speed? Well, instantaneous speed is how fast an object is going at a specific moment in time. If you were driving down the road and you are in a 55 mile an hour speed zone and you're going 80, and the police officer clocks you at 80, pulls you over, he was, well, you think about it, was he calculating with the radar gun there, was he calculating your average speed, or was he calculating your instantaneous speed? Well, hopefully you would say that it was instantaneous, because it was at that specific moment that his radar gun clocked you. It was not over a long period of time that he was getting your speed. So this instantaneous concept would be at that instant, that moment, how fast you were going. Again, not a vector quantity. And then average speed, of course, is your distance covered over a total trip time. So you might be on a road trip to the beach, or you might be on a plane trip to California or wherever. And you wanted to calculate your average speed. Well, of course, your average speed is going to be your total distance that you traveled over the total time it took. If at one point on the road trip you're going 55 miles per hour, that does not mean every second of the trip you were traveling at 55. It means an overall value. It's an average value for the speeds that you were going throughout the trip. You may have been going 5 miles per hour at one point. You may have been going 75 miles per hour at another point. So your instantaneous speeds could be changing. Now, could your instantaneous speed match your average speed at that point in the trip? Of course it can. Of course it can. I might be going 55 miles per hour at a certain time, and then right after that, slow down or speed up. But my overall average speed, 55, could have matched my instantaneous speed during the trip. There's some relative values for those of you that struggle with how a meter per second relates to a miles per hour. So if you're traveling down the road and you're going 75 miles per hour, that's 33 meters per second. So 33 meters per second is going pretty fast. And of course, 44 meters per second would be going at 100 miles per hour. And then here you're some kilometers per hour. And if you look at your odometer in your car, your speedometer in your car, you should, maybe it's in small font, it might be almost impossible to read, but you can still make out how many kilometers per hour you're going. Usually it's miles per hour is the most common that you'll see on the speedometer, but then somewhere it should also say kilometers per hour, usually. It's not always the case, but usually you can see both. So velocity, we know that that is speed in a given direction, and we say that speed would count as the magnitude, and then we would add a direction at the end. So if I'm going 5 miles per hour or 65 meters per second, both of those values are considered to be speeds. And then if I said positive 5 miles per hour or negative 65 meters per second, we would expect those to be called velocities, because now not only are they speed values, the magnitude, but they're also directions, so that makes them velocities. And of course, here's our coordinate plane for giving directions on velocity. So just to review, velocity is a vector quantity. It has magnitude with direction. Speed is a scalar quantity, and it has only magnitude. Average velocity, again, our formula from earlier. Let's be extra careful here. We say delta x is the same thing as saying x sub f minus x sub I. Remember, delta x is the change in position. X sub f is the final position. X sub I is the initial position. And then delta t means change in time. So that's t sub f minus t sub I. So final time minus initial time. And if you take both of those values, xf minus xi, over tf minus ti, that is a formula for average velocity. And of course, you could also say average velocity is delta x, which means change in position, over delta t. And that's the way it's written in your formula sheet, although I think I may have written it like that as well. And remember, the displacement value can be positive or negative, or east or west, north, south, up, down, left, right. But the time value is always going to be positive, always positive. Time never has a negative value unless you own a time machine. How about changing velocity? Well, we haven't gotten into acceleration yet, but when velocity changes, there are two ways that it can change. And a good way to think about it is your body notices when velocity changes. You feel velocity change. And the way it works is this. Either the speed or the direction changes. Doesn't have to be both, but one or the other. I mean, it could be both, but it can be one or the other. So if you're speeding up or you're slowing down, you are going through a change in speed, which means your velocity is changing. If you take a sharp right turn in a car, your direction is changing. Your velocity is changing. So a car moving in a circle, like the one you see here, it might be going, say, 10 miles per hour in a circle. You cannot say, well, 10 miles per hour in a circle is constant. Yes, the speed is constant, but the direction is constantly changing. If you think of circular motion, at this point, what's the direction of the car? It's that way. At this point, what's the direction of the car? It's that way. At this point, what's the direction of the car? It's that way. What's this direction? It's going that direction. So during a circular motion, when the car is moving in a circle, you always have a changing direction. So if you're traveling in a circle, even though your speed's constant, your velocity is changing. And we have a special name for changing in velocity, and that is acceleration, which we'll get to in the next unit. So that's the idea. Change in velocity means acceleration. So here we're looking at a position time graph where position is on the y-axis and time is on the x. And what we can see from the formulas down here is that this idea of velocity can be derived from a graph. We know that velocity is the change in position over the change in time. And if you read it from left to right, we know that the slope of a graph, which is abbreviated with a letter m, is the rise over the run. And of course we can see that the rise would be the change in the y-axis. So as this goes up, we know that y is changing. And x is changing along the x-axis. Well, if we know that the change in y is equal to the change in position, we can write delta x. And if we know the change in the x is the change in time, we can write delta t. And you can therefore derive from a position time graph this idea that the velocity is equal to the slope of the graph. So it should be very easy to see, I think, this idea. So in this problem, we have a race car driver that's just completed the Daytona 500. He finished the 500-mile race in 3.5 hours. And just for the sake of easiness here, just to make sure that we don't overthink the problem, we're going to say that the starting point and the stopping point were the same exact point. So if you look at the blue line in the picture, we're going to say that's the starting and ending point for the car. So what do we know? One of the things that's important with physics is you always write down what you know. Well, 500-mile race, to me, if you're trying to find the velocity, the change in position, well, let's think about this. The final position was here, so we could maybe call that point 0 meters. And the initial position was the same point, 0 meters. The total time, total change in time, was 3.5 hours. And if you think about this idea of velocity, we know that velocity, it's very important to distinguish between distance and the displacement. The displacement in this example is xf minus xi. Well, that would end up being 0 minus 0. And of course, we don't need to get our calculators out for that. We know that that's going to be 0. So if you're trying to find the velocity in this problem, it's going to be delta x over delta t. It's going to be 0 meters over 3.5 meters. And of course, that's 0. So this is kind of a trick question. You were asked to find the average velocity for this car race, and the displacement is 0. But the speed, a little different. The distance, now remember, distance, not displacement. The distance is 500 miles. The change in time is still 3.5 hours. That hasn't changed. And we know that speed equals the distance over the time. So the distance is 500. The change in time is 3.5 hours. And we know that when we divide our 500 by the 3.5, we get 142.857. And if I'm looking at sig figs, I would say the 3.5 might cause us to round all the way up to 2 sig figs. That would be the 4, so we would look at it as 140 miles per hour. And do we need a direction for our answer? No, we do not, because speed is just a scalar quantity. So in this case, the speed is 140 miles per hour, while the average velocity is 0. All right, our next example, how much time in minutes would it take a bobsled to cover a 5,000 meter course if it travels at 22 meters per second? 5,000 meter course, and we are given a couple of things here. We're given the distance. Now I'm going to write distance instead of displacement because the way that this is given, we notice it's given without a direction. It says it travels 22 meters per second. So we would say that that is a speed and not a velocity. We know that we're trying to find t, and we know that's going to be in seconds. So what formula are we going to go look for? Well, we need a formula that has speed, distance, and time, and we know that there is one. Speed equals distance over time. And we're going to rearrange here to get that t equals distance divided by speed. Be very careful here. A lot of students will tend to want to just multiply to get this answer. If you're trying to isolate t, multiply both sides by t, you get ts equals d. And then if you want to get rid of s, you got to divide by s. So if t equals d over s, and d is 5,000 meters, and s is 22 meters per second, what are we going to get? We divide 5,000 by 22. We end up with 227.27 repeating seconds. Of course, we have to remember here, this question asks us to find minutes. Made a mistake up here. It should be minutes is what we're looking for, not seconds. And how are we going to get these seconds to minutes? Well, we know that in 1 minute there is 60 seconds. And that means we're going to divide our answer by 60. And we're going to write 3.7878 repeating minutes. And if I'm looking at sig figs here, I know I'm going to go with 2. And that would be 3.8 minutes for my answer. 3.8 minutes for the bobsled to cover the 5,000 meter course. All right, our last notes sample problem says John Cleese begins his southward journey. First, he walks south at 6.5 kilometers per hour. Let's call that V. Let's call that V1. 6.5 kilometers per hour south. And he does this for 1.1 hours. We'll put T1 is 1.1 hours. Then he stops to take a nap for 18 minutes and then continues on his southward, and then continues south at 5.5 kilometers per hour for 1.2 hours. So let's call the second part where he takes a nap, let's call that V2, and of course his velocity would be 0 because he was taking a nap, he wasn't doing any moving. And 18 minutes, we're probably going to need to change that. And since the velocities are given in kilometers per hour, let's change that to hours. So T2 is going to be 18 minutes, but we're going to say that in 1 hour there's 60 minutes. So in that case, the time in hours for the second part of the trip is 0.3 hours. And for V3, that was the last part of his journey. V3 would be 5.5 kilometers per hour. And that T3 would be 1.2 hours. Question A, what is his average velocity for the whole trip? Well, his average velocity for the whole trip, we would need to know what? What would we need to know for average velocity? We would need to know the total displacement divided by the total time. Well, let's see. Do we know his displacement for any of the trips? We do not. So it's probably a better idea here to take a look at a second problem. What was his displacement for the whole trip? Because then we can take our answer to B and use it to help us solve for A. You could do A first, but you're going to have to get the answer to B to do A. So let's go ahead and see if we can figure out what his total displacement was. For the first part of the trip, the total displacement, I'll just put total displacement, is going to be here, total change in position. We know that average velocity equals the change in x over the change in time, which means the change in x is going to be v times t. So let's take a look at the first part of the trip. I'll put little ones here so we know which one we're talking about. V1 is 6.5 kilometers per hour. T1 is 1.1 hours. Which means if we were going to try to find the total displacement for the first part of the trip, it would end up being 7.15 kilometers. So, and that is delta x1, change in position 1. For our second part of the trip, what occurred in blue, what would be the total displacement? Well, do we actually need to do any math here? His velocity was 0. So can he have any displacement if his velocity was 0? I don't think so. So we could show it in math form here. We could say, all right, v equals delta x over t, and delta x2 equals v2 times t2, and v2 is 0, and t2 was what? 8.3 hours, which means that this total displacement for part 2 was 0 meters, or 0 kilometers, however you want to describe it. And then part 3, we know the velocity, we know the time, so let's go ahead and set out to find the displacement for part 3. Part 3 displacement would be the total velocity, in this case was 5.5 kilometers per hour, times our total time for part 3, 1.3 hours, and 5.5 times 1.2, sorry, that should be a 2 right there. 5.5 times 1.2 gives us 6.6 kilometers, and that is delta x3. So how are we going to find our total displacement? Well, we're going to add them all up. Our total displacement is going to be the change in time, or excuse me, the change in position for 1, plus the change in position for 2, plus the change in position for 3. So that's going to be delta x1, which was 7.15 kilometers, plus delta x2, which was 0, plus delta x3, which was 6.6 kilometers. And our total displacement, I'm just going to write delta x sub t for total, is going to be 14 kilometers. And do we need a direction? Well, we were asked to find the displacement, so we certainly do. All directions were south, so I'm just going to put a south there. under that part. All right, 14 kilometers south. Now, of course, we did do some rounding there for the addition. 14 kilometers south is the answer to letter B. So now we go back to A. And what did A ask us to find? It was what was the average velocity for the whole trip? Well, the average velocity is going to be the total displacement divided by the total change in time. Well, the total displacement we just solved for that, it was 13.75. Again, I rounded the 14. But if I'm going to solve for a second answer, I don't need to round one answer to get another answer. That's not good for sig fig rules. So 13.75 is what we get when we add them up and didn't round for part B. Total time, what's that going to be? Well, let's think about this. Do we know all the times? I think we do. 1.1, 0.3 hours, 1.2. So the total time is going to be 1.1 hours plus 0.3 hours plus 1.2 hours. And that gives us a total of 13.75. That gives us a total of 2.6 hours when we add those up. So now we're going to take 13.75, we're going to divide it by 2.6, and we end up with 5.3 kilometers per hour is the average velocity. Now, are we missing anything? Is there something that we need to put in our answer that would cause us right now to get points off? And hopefully you're thinking about that vector quantity. If it is a vector quantity, it better have a direction. And 5.3 kilometers per hour does not have a direction. All of these journeys were to the south, so if I just put S, I'm good to go. One more note of caution. A lot of students have, in the past, asked about adding up all of the speeds and dividing by 3. And when you do that, if you add up 5.5 kilometers plus 6.5 and then divide it by the number 3, you get 4.58, I believe. So you don't get 5.3. So you cannot do that. The only way you could do that is if all of the times for each speed were equal times. Think of it like a weighted grade average. If you have one part of your grade is worth 50% and the other part is worth 50%, you add them up and you divide by 2 to get your average. But if one part of your grade is 70% and the other part of your grade is 30%, you can't add them up and divide by 2 to get your average. You have to weight the 70%. So when you're doing a problem like this, you cannot just add up the velocities and divide by however many velocities there were, because the time that you were traveling at those velocities were not equal. So be careful about things like that. It seems obvious that, oh, well, I could just add them up and divide by 3, but you can't do that here. You have to take into account that they were not for the same amount of time.